Hello there and welcome back to the Science Sleepy Minds. Picture this. You're standing barefoot on a sun-drenched patch of grass somewhere in the middle of July. The blades are warm and slightly damp beneath your toes, and the sunlight is pressing against your shoulders like a gentle golden hand. You can feel the heat on the tops of your ears, on the bridge of your nose, on the little strip of skin between your watch and your wrist. Everything about this moment tells you the sun is generous, powerful, and magnificently hot, and it is. The surface of that glowing ball sitting roughly 93 million miles away is close to 5,500 degrees Celsius. Its core is burning at around 15 million degrees. If you could somehow scoop a teaspoon of the sun's center and set it down in your backyard, you probably would not survive the experience, and neither would several surrounding zip codes. Yet here is the thing that should keep you awake tonight. Well, at least for a little while. The space between you and that raging furnace, the vast stretch of nothing that sunlight has to cross before it tickles your skin, is absurdly bone-achingly cold. Or is it? That question is what we are going to unravel together, slowly and gently as you settle in for the night. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. If you feel like it, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those little postcards from around the world. Someone last week was tuning in from a fishing boat off the coast of Norway at 2 a.m, which honestly sounds like the most perfect place to fall asleep to a story about the cold vacuum of space. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your head back and look up. The sky, if we are keeping our July daydream alive, is that deep, unreasonable blue that seems to go on forever. But it does not go on forever. That blue is a thin shell of gas clinging to a rocky ball, and beyond it lies something that has puzzled scientists, philosophers, and probably a few restless children staring out of car windows for centuries. Space. The big empty. The great nothing. Call it whatever you like, but the point is this: it is not what you think it is, and it is certainly not as straightforward as hot sun, cold space, end of story. If it were that simple, we would not need 20 sections and a cozy blanket to work through it. Let us start at the most obvious place, which is that enormous luminous object you were just squinting at. The sun has been a source of fascination for as long as humans have had eyes and enough free time to wonder about things. The ancient Egyptians worshipped it as Ra, a falcon-headed god who sailed across the sky in a boat every single day, which is a commute that makes your morning drive look laughably easy. The Greeks had Helios, who drove a chariot pulled by 4 fiery horses, because apparently one mode of celestial transport was not dramatic enough. And in 1543, Copernicus rather bravely suggested that the Earth revolved around the sun and not the other way around, which did not go over well at dinner parties for quite some time. Historians still argue whether Copernicus delayed publishing his work out of fear of religious backlash, or simply because he was a perfectionist who kept tweaking his math. Either way, the man waited until he was practically on his deathbed to release the book, which is the ultimate example of procrastination meeting courage. But here is a quirky little detail you might not know. Before anyone understood nuclear fusion or spectroscopy, or any of the tools we use today to study the sun, a handful of 19th century scientists genuinely believed the sun might be burning coal. William Thomson, Lord Kelvin himself, one of the most brilliant physicists in history, calculated that if the sun were a giant lump of coal burning in oxygen, it could only last about 5,000 years. He was magnificently wrong, of course, but the fact that he even ran the numbers tells you how desperate people were to explain where all the heat was coming from. The real answer, as you probably know, involves nuclear fusion. hydrogen atoms smashing together under tremendous pressure and temperature to form helium, releasing energy in the process. We will sink deeper into that furnace in the next stretch of our journey, but for now, just hold on to the image. A ball of gas so massive that its own gravity crushes atoms together at its core, and the result is light and heat on a scale that your brain genuinely cannot process. Now, here is where the paradox sneaks in and taps you on the shoulder. You're feeling that warmth on your July skin because energy from the sun travelled all the way across space to reach you. It left the sun's surface, crossed roughly 150 million kilometres of vacuum, punched through Earth's atmosphere, and landed on your nose. That is an astonishing journey. But if the sun is so ferociously hot, and it is sending all of this energy outward in every direction, why is the space in between so cold? Why is it that an astronaut floating halfway between here and the sun would not be basking in a pleasant tropical warmth, but would instead be dealing with conditions that make Antarctica look like a beach resort? The answer, as you might suspect, is not about the sun being stingy with its heat. The sun is fantastically generous. It is about what is, or rather what is not, out there to receive it. And to understand that, you need to understand what temperature actually means, which turns out to be a much stranger question than you might expect. You shift your weight on that warm grass. A breeze moves across your arms. Somewhere nearby, a cricket begins to chirp, because crickets have an unerring instinct for moments that need a soundtrack. You're about to take a journey from this patch of sunlit ground all the way to the emptiest reaches of the cosmos, and along the way, you're going to discover that heat, cold, and temperature are not quite the simple, reliable concepts you grew up believing they were. They are slippery, they are context-dependent, and in the vacuum of space they become downright philosophical. So settle in. Pull that blanket a little higher if you need to. We have a long, gentle road ahead, and the first stop is a peculiar one. We're going to shrink you down, way, way down, to the level of individual atoms, because that is where the real story of temperature begins. You feel yourself shrinking. Not in a painful, alarming way, but in that slow, dreamy manner where the grass beneath your feet begins to look less like a lawn and more like a forest of towering green columns. The blades rise above you like cathedral pillars, and the dewdrops clinging to their sides become shimmering boulders of water, each one reflecting a tiny, distorted version of the sky. You keep going, smaller. The dewdrops are now lakes. The surface of each one is trembling, alive with motion, and as you drop below the threshold of the visible, you begin to see why. Everything around you is moving, not calmly, not occasionally, but ceaselessly, and with a kind of frantic, jittery energy that makes a toddler on a sugar rush look like a Buddhist monk in deep meditation. This is the world of molecules, and the first thing you notice is that nothing is still. The water molecules in that dewdrop are tumbling over one another, spinning, vibrating, bouncing off each other in every conceivable direction. The nitrogen and oxygen molecules in the air around you are doing the same, zipping past at hundreds of meters per second, colliding, ricocheting, colliding again. It is chaos. Beautiful, fundamental, absolutely essential chaos. And this chaos, this constant jiggling and crashing of tiny particles, is what temperature actually is. That might sound like an oversimplification, but it is not. When you touch a hot cup of tea and say it is hot, what you are really detecting is the fact that the molecules on the surface of that cup are vibrating and moving with a lot of kinetic energy. They bump into the molecules of your skin, transferring some of that energy, and your nerve endings translate that transfer into the sensation you call heat. When you press your hand against a cold window in winter, the opposite is happening. The glass molecules are moving relatively slowly, and energy is flowing out of your warmer hand and into the cooler glass. You feel that loss of energy as cold. So temperature, at its most fundamental, is just a measurement of how fast particles are jiggling around. Fast jiggling equals hot, slow jiggling equals cold. No jiggling at all would be absolute zero, but we will visit that eerie concept much later tonight, when you are even drowsier. Now here is where it gets interesting, and where the whole mystery of cold space starts to make a lot more sense. Temperature requires stuff. It requires matter. It requires molecules or atoms or particles of some kind to be doing the jiggling. If you remove the particles, the concept of temperature does not just drop to zero. It essentially stops meaning anything at all. Imagine trying to measure the average height of people in an empty room. The question is not answerable. There are no people. The average is not zero. It is undefined. Temperature in a perfect vacuum works the same way. If there are no particles, there is no motion to measure, and the thermometer you brought along has nothing to interact with. It just floats there, looking confused, which is roughly how you would look too. This idea took a surprisingly long time to crystallize in scientific thought. The ancient Greeks, clever as they were, had some wonderfully wrong ideas about heat. Aristotle believed that fire was one of the four fundamental elements alongside earth, water and air, and that hot and cold were intrinsic qualities that objects simply possessed. A stone was cold because coldness was part of its nature. A flame was hot because hotness was part of its nature. It sounds charmingly naive now, but this framework dominated Western thinking for nearly 2,000 years, which is a genuinely humbling reminder that being wrong with enough confidence can carry you a very long way. Historians still argue whether Aristotle's elemental theory held on so long because it was intuitively satisfying, or because challenging Aristotle was essentially a career-ending move in medieval academia. Probably both. The real breakthrough came in the 17th and 18th centuries, when scientists like Robert Boyle, Daniel Bernoulli, and later James Clerk Maxwell and Ludwig Boltzmann began developing what we now call the kinetic theory of gases. The idea was radical for its time. Heat's not a substance, not a fluid, not an intrinsic quality. It is motion. The faster the particles in a substance move, the hotter it is. Bernoulli, in 1738, even proposed that gas pressure was caused by molecules smashing into the walls of their container, which was met with a reaction that can be politely summarized as, "That is adorable, Daniel, but no." It took another century for the idea to gain mainstream acceptance, partly because no one could actually see molecules, and asking people to believe in invisible bouncing balls required a certain leap of faith. And here is a quirky little tidbit to tuck under your pillow. Before kinetic theory won the day, the dominant explanation for heat was something called caloric theory, which imagined heat as an invisible, weightless fluid called caloric that flowed from hot objects to cold ones. It was proposed in its most refined form by Antoine Lavoisier, the father of modern chemistry, who was otherwise a staggeringly brilliant man. He listed caloric as an element on his table of elements, right alongside oxygen and hydrogen. You could almost forgive the error. If you watch heat flow from a hot cup of tea into cool air, it genuinely does look like something is flowing. Caloric theory eventually collapsed under the weight of experiments it could not explain, but it hung around in textbooks well into the mid-1800s, like a house guest who does not realise the party ended hours ago. So where does this leave you, floating among the molecules in your shrunken state? It leaves you with a crucial piece of understanding. Temperature is motion. Motion requires matter. And space, that vast expanse between the sun and the earth, is almost entirely empty. Not perfectly empty. There are a few stray hydrogen atoms per cubic centimetre in interplanetary space, and we will talk about those lonesome wanderers soon, but so close to empty that the notion of temperature becomes gossamer thin. When someone tells you space is cold, what they usually mean is that if you put an object in space, away from any star, it would eventually radiate away its own heat and drop to a very low temperature. But the space itself is not cold in the way a freezer is cold. A freezer is full of cold air molecules that actively pull heat from your ice cream. Space has almost nothing in it at all. You hover there for a moment among the vibrating molecules of Earth's atmosphere, watching them dance. It is strangely beautiful, this invisible ballet that gives you every warm breeze and every chilly morning you have ever felt. And now you understand that the sun, sitting out there in its ferocious glory, is not heating space. It is sending energy through space. What happens to that energy when it arrives somewhere, when it hits a planet, a rock, an astronaut's visor? That is where the story of hot and cold truly plays out. The void between here and there is just the silent, empty stage. You leave the world of molecules behind and begin to grow again, but not back to your normal size. Instead, you keep going. You grow past the dewdrop, past the grass, past the rooftops and the clouds, and you do not stop until the earth is a blue-green marble beneath you, and the sun is filling your vision like the mouth of an enormous furnace. You are heading inward now, toward the center of the star that makes life on your little planet possible, and you should know up front that what you are about to witness is violent, extreme, and completely indifferent to your comfort. The sun does not care about you. It is not trying to warm you or light your way or give you a nice tan. It is simply doing what physics demands, and what physics demands in this case is a controlled thermonuclear explosion that has been running without interruption for roughly 4.5 billion years. You pass through the corona first, that ghostly halo of superheated plasma that extends millions of kilometers into space, and which, paradoxically, is far hotter than the surface below it. We will wrestle with that particular oddity later, so for now just note it and move on. Next comes the chromosphere, a thin, reddish layer that you can sometimes see during a total solar eclipse, glowing like a ring of fire around the moon's silhouette. Then you hit the photosphere, the visible surface, where the temperature is a relatively modest 5,500 degrees Celsius. Relatively modest is doing a lot of heavy lifting in that sentence, because 5,500 degrees is still hot enough to vaporize every material you have ever touched, including the tungsten in your light bulbs and the diamonds in whatever jewelry you may or may not own. But compared to where you are going, the photosphere is practically a cool breeze. You sink deeper, through the convective zone, where enormous columns of plasma rise and fall like a lava lamp the size of a planet, carrying heat from the interior to the surface in great churning loops. The plasma here is thick and turbulent, glowing white and gold, and you can feel the density increasing as you descend. Then you pass into the radiative zone, a region so dense that light itself struggles to move through it. Photons here do not travel in straight lines. They are absorbed and re-emitted by the tightly packed particles, bouncing in random directions, taking what physicists charmingly call a random walk. A single photon generated in the core of the sun can take anywhere from 10,000 to 170,000 years to stumble its way through the radiative zone and reach the surface. Let that settle for a moment. The sunlight warming your face on a summer afternoon left the core of the sun before the last ice age, before humans painted bison on cave walls, before language, before agriculture, before the invention of the wheel. It has been pinballing through the sun's interior for millennia, and it only just arrived. And then you reach the core, the heart of the beast. Here the temperature is approximately 15 million degrees Celsius, and the pressure is about 250 billion times the atmospheric pressure at Earth's surface. These numbers are so large that they stop being meaningful in any human sense. You cannot feel 15 million degrees. You cannot imagine 250 billion atmospheres. Your brain, which evolved to assess whether a berry is ripe and whether that rustling in the bushes is a predator, simply does not have the hardware for this. But you can understand the process that happens under these conditions because the process at its core is elegant and almost absurdly simple. Hydrogen nuclei, protons essentially, are moving so fast and are squeezed so tightly together that they overcome their natural electromagnetic repulsion and fuse. Two protons smash together, and through a chain of steps involving positrons, neutrinos and gamma rays, they eventually form a nucleus of helium-4. The helium nucleus has slightly less mass than the original protons that went into making it. That missing mass has not vanished. It has been converted into energy in accordance with the most famous equation in all of physics, the one that Einstein scribbled down in 1905 and that every college student has pinned to a poster at some point. Energy equals mass times the speed of light squared. The speed of light squared is an enormous number, which means even a tiny amount of missing mass produces a staggering amount of energy. Every single second, the Sun converts roughly 600 million tons of hydrogen into helium, and in the process, about 4 million tons of matter simply become energy. 4 million tons per second, vanishing into light and heat and neutrinos, and the Sun has been doing this for 4.5 billion years without so much as a coffee break. Here is a mainstream historical fact that puts this into perspective. In the mid-19th century, well before anyone understood nuclear fusion, scientists were genuinely baffled by how the Sun could keep shining. Lord Kelvin and Hermann von Helmholtz proposed that the Sun was slowly contracting under its own gravity, converting gravitational potential energy into heat, a mechanism now called the Kelvin-Helmholtz mechanism. Their calculations suggested the Sun could sustain this for about 20 to 30 million years, which seemed like a comfortably long time until geologists and biologists started insisting that the Earth was far older. Charles Darwin's theory of evolution required hundreds of millions of years for species to diversify, and geologists studying rock layers were reaching similar conclusions. A feud erupted between physicists and geologists that lasted decades. Historians still argue whether Kelvin's stubbornness on the age of the Sun set back geological science, or whether it simply motivated geologists to sharpen their evidence. Either way, the dispute was not resolved until the early 20th century, when Hans Bethe worked out the nuclear fusion reactions that power the Sun, and suddenly the timescale became billions of years. Everyone could relax. And here is something delightfully odd. The Sun is not perfectly efficient. For all its fury, the energy output per unit volume of the Sun's core is roughly the same as a compost heap. A pile of rotting garden waste generates about the same amount of heat per cubic meter as the centre of the Sun. The difference, of course, is that the Sun has an absurd amount of volume. Its core is enormous, so all those tiny contributions add up to a luminosity of about 384 trillion watts. But if you could isolate a single cubic meter of solar core material and put it in your garage, you would be underwhelmed. It would be warm, sure, but not dramatically more so than a well-maintained compost bin. This is one of those facts that makes astrophysicists grin, and everyone else squint suspiciously, but it is absolutely true, and it is a lovely reminder that the universe often achieves its most spectacular results, not through intensity, but through sheer, incomprehensible scale. You float in the core for a moment, surrounded by the ghostly blue-white glow of plasma so dense it behaves more like a liquid than a gas. Neutrinos stream past you in uncountable trillions, passing through your body as if you were not even there. Because to a neutrino, matter is barely an inconvenience. Energy is being born all around you, in the form of gamma-ray photons that will begin their long, tortured journey outward through the radiative zone, a journey that will take longer than most civilizations last. and you begin to appreciate the first half of tonight's paradox. The sun is not just hot, it is unfathomably, relentlessly, almost absurdly hot. It is a nuclear furnace on a cosmic scale. The question now is what happens to all that energy once it finally escapes? The energy claws its way outward. You already know that a photon born in the core does not simply zip to the surface in a straight line. It stumbles, drunk on collisions, absorbed and re-emitted by one particle after another, in a journey so tortuous that calling it inefficient would be the understatement of several millennia. But eventually, after thousands or even hundreds of thousands of years of this subatomic pinball, the photon reaches the convective zone, where the physics changes. Here, instead of radiation doing the heavy lifting, great cells of plasma physically rise and fall, carrying energy upward the way boiling water carries heat from the bottom of a pot to the surface. You can see evidence of the convection if you look at the sun through a properly filtered telescope. The photosphere is covered in a pattern called granulation, a mosaic of bright cells surrounded by darker boundaries, each cell about 1,000 kilometers across. The bright centers are where hot plasma is rising, and the dark edges are where cooler plasma sinks back down. The whole surface looks like a pot of simmering oatmeal, a comparison astrophysicists have been making for decades, probably ruining breakfast for a number of them. Once the energy reaches the photosphere, that visible surface sitting at around 5,500 degrees Celsius, the photons are finally free. After their impossibly long random walk through the interior, they break loose and fly outward into space at the speed of a light. 300,000 kilometers per second. No more collisions, no more detours, just pure unobstructed travel through the vacuum. And this is the light that, about 8 minutes and 20 seconds later, hits the Earth, warms your skin, powers photosynthesis, and generally makes your existence possible. But light is not a single thing. The photons leaving the sun span an enormous range of wavelengths, from short, energetic ultraviolet rays to the visible spectrum you perceive as colour, to longer, lazier infrared waves you feel as warmth. The sun's peak emission is actually in the green part of the visible spectrum, which surprises almost everyone. You would think the sun would peak in yellow, given that every child draws it with a yellow crayon, but no. It appears white or yellowish because it emits across the entire visible spectrum simultaneously, and your brain blends those wavelengths together. Earth's atmosphere then scatters shorter blue wavelengths, more than longer red ones, which is why the sky is blue, sunsets are orange, and the sun itself looks yellow, even though it is technically lying to you about its true colour. Now here is an elegant piece of history. In 1814, a German optician named Joseph von Fraunhofer passed sunlight through a high-quality prism. Newton had done something similar in 1666, but Fraunhofer had far more precise equipment. When he spread the sun's spectrum out, he noticed that the rainbow was not continuous. It was interrupted by hundreds of thin, dark lines where specific wavelengths were missing. He catalogued over 570 of them. Decades later, Gustav Kirchhoff and Robert Bunsen figured out that the dark lines corresponded to chemical elements in the sun's outer atmosphere absorbing particular wavelengths. The sun was sending us its chemical fingerprint in every beam of light. We could read the composition of a star 93 million miles away without visiting it. Historians still argue whether Fraunhofer fully grasped the significance of what he found or viewed the lines primarily as calibration tools for his optical instruments. Either way, his work birthed astrophysics. And here is the quirky tidbit. Fraunhofer was an orphan trapped in a building collapse as a teenager. The accident drew attention from prominent citizens, including the Prince Elector of Bavaria, who helped him access education and optical workshops. Without that collapsing building, spectroscopy might have been delayed by decades. Science sometimes pivots on the strangest accidents. So the energy leaves the sun as electromagnetic radiation, a broad spectrum of photons racing outward in all directions. And this is the critical hinge of tonight's entire mystery. Those photons are energy. They are packets of electromagnetic radiation travelling at the speed of light through vacuum. But they are not heat. Not yet. Heat, as you learned when you were molecule-sized, is the kinetic energy of particles. It is the jiggling. Photons travelling through empty space are not making anything jiggle, because there is nothing there to jiggle. They are potential warmth, energy in transit, a promise of heat that will only be fulfilled when they strike something. A planet, an asteroid, a speck of dust, an astronaut's glove. Until that moment of contact, they are silent travellers crossing an empty stage. This is why the space between the sun and the earth is not hot. It is flooded with energy, absolutely drenched in it. Photons stream through every cubic centimetre of interplanetary space in unfathomable numbers. But because there is virtually no matter out there to absorb that energy and convert it into thermal motion, the energy simply passes through. It is like standing in a rainstorm made of light where none of the drops ever land. The rain is real, the energy is real, but without a surface to catch it, there is no puddle, no wetness, no warmth. You watch the photons streaming away from the sun's surface, an uncountable flood spreading outward in a sphere that grows larger with every passing moment. As that sphere expands, the energy spreads thinner. By the time it reaches Earth, the intensity has dropped to about 1,360 watts per square metre, a quantity called the solar constant. By Jupiter, 5 times farther away, it is about 50 watts per square metre. By Neptune, barely 1. The energy does not disappear. It dilutes, spreading across an ever larger area, like a single pat of butter scraped across an increasingly enormous piece of toast. Beyond Neptune, beyond the Kuiper belt, that energy keeps travelling, growing fainter, until it is an almost imperceptible whisper in the dark. You find yourself sitting beside a campfire. Not a real one exactly, but the kind your mind conjures when it needs a simple, familiar image to anchor something complicated. The flames are low and orange, licking lazily at a stack of logs, and you are close enough to feel the warmth pressing against your shins and the fronts of your hands. Behind you, the night air is cool against your neck. This little scene, this ordinary moment of sitting by a fire, contains everything you need to understand why the sun's heat does not warm the emptiness of space. Because right here, in the flicker of these flames, all 3 methods of heat transfer are happening at once, and only one of them can survive the void. The first is conduction. You know this one instinctively, even if you have never heard the word. It is what happens when you touch a hot pan and yelp. Energy transfers directly from one material to another through physical contact, molecule to molecule, each one bumping its neighbour and passing along kinetic energy like a crowd doing the wave at a stadium. The hot pan's molecules are vibrating furiously, and when your skin molecules make contact, they start vibrating faster too, and your brain interprets that as pain and regret. Conduction requires matter to be touching other matter. No gaps, no empty space, just a continuous chain of particles handing off energy. In the context of space, conduction is essentially useless. There is nothing touching anything out there. The sun cannot conduct its heat to the earth because there is no physical bridge of material connecting them. It would be like trying to pass a cup of tea to someone across a canyon by holding it out and hoping for the best. The second method is convection, and you're feeling it right now in the way the warm air from the campfire rises and swirls around you. Convection is heat transfer through the movement of fluids, which in physics means both liquids and gases. The fire heats the air directly above it. That air becomes less dense and rises. Cooler air rushes in to replace it, gets heated in turn, and rises as well, creating a shunhuan that distributes warmth through the surrounding atmosphere. This is why the second floor of a house is usually warmer than the first. This is why boiling water circulates in a pot. And this is the same process that churns plasma in the sun's convective zone. Those enormous cells of rising and sinking material you saw when you were diving toward the core. But convection, like conduction, requires a medium. It needs stuff to flow. In space there is no air, no water, no fluid of any kind. Convection cannot operate in a vacuum any more than you can swim through an empty swimming pool. You could try, but you would just look silly and bruise your knees, which leaves radiation. The third method, the lonely survivor. And you are feeling this one too, even if you do not realize it. Hold your hands out toward the campfire. That warmth on your palms is not conducted heat, because the air between you and the flames is a relatively poor conductor. It is not convected heat, because the warm air is rising up, not streaming horizontally toward your hands. What you are feeling is infrared radiation, electromagnetic waves emitted by the hot flames and coals, travelling through the air at the speed of light and being absorbed by your skin. Radiation does not need a medium. It does not need molecules or atoms or any form of matter between the source and the receiver. It travels perfectly well through the vacuum of space, which is exactly why sunlight can cross 150 million kilometers of nothing and still warm the Earth. This distinction is the key that unlocks tonight's entire puzzle, so let it sink in while the campfire crackles. The sun produces an enormous amount of energy through nuclear fusion. That energy travels outward as electromagnetic radiation. It crosses the vacuum of space effortlessly, because radiation does not need a medium. But when people say space is cold, they are talking about what would happen to an object placed in that vacuum, away from any source of radiation, without molecules around it to transfer heat through conduction or convection. The only way the object can gain or lose energy is through radiation, and if it is far from any star, it will slowly radiate away its own thermal energy into the void, getting colder and colder with nothing to replenish what it loses. Here is a historical fact that ties this together beautifully. The understanding that heat could travel through a vacuum was not always accepted. In the early 1800s, many scientists still subscribed to caloric theory, that invisible heat fluid you met a few sections ago. The caloric model struggled to explain how heat from the sun could cross empty space, and some natural philosophers proposed that space was not actually empty but filled with a mysterious substance called the luminiferous ether, a medium through which light and heat waves supposedly propagated. The ether was imagined as weightless, invisible, perfectly transparent, and completely frictionless, which is a suspiciously convenient list of properties for something you cannot detect. Historians still argue whether the ether concept was a reasonable hypothesis given the knowledge of the time, or whether it was always a placeholder that scientists clung to, because the alternative, waves travelling through nothing, felt philosophically uncomfortable. The famous Michelson-Morley experiment of 1887 effectively killed the ether by showing that light speed did not change regardless of Earth's motion through this supposed medium, paving the way for Einstein's special relativity. And here is your quirky fringe tidbit for this stretch. Before Michelson and Morley built their interferometer in a basement in Cleveland, Ohio, some proponents of the ether suggested it might have unusual mechanical properties, behaving like a solid for high-frequency vibrations, but like a fluid for slow movements. Lord Kelvin himself speculated that the ether might be a kind of cosmic jelly, rigid enough to support light waves, yet soft enough for planets to glide through it without resistance. The image of Jupiter ploughing silently through invisible cosmic jelly is one of the more endearing dead ends in the history of physics. You let the campfire die down in your mind, the embers glowing a deep sleepy red. Conduction needs contact, convection needs fluid, only radiation crosses the void. And that single fact explains why the sun can be so ferociously hot, while the space around it remains so hauntingly empty of warmth. You leave the campfire behind and drift upward again, past the atmosphere, past the last thin wisps of air that cling to the earth like a child clutching a parent's hand, and you find yourself floating in the space between the earth and the moon. It is quiet here. Not quiet in the way a library is quiet, where you can still hear the hum of the air conditioning and the soft rustle of turned pages. Quiet in a way that has no comparison in your earthbound experience. There is no sound here because there is nothing to carry it. No air molecules to compress and expand in waves. No medium for vibration. If you screamed, which you would have every right to do given your current predicament, the sound would not travel a single centimetre from your lips. It would die inside your helmet, unheard by the universe, which is both poetic and mildly insulting. But the silence is not what we are here to talk about. We're here to confront the emptiness, and empty it truly is, in a way that your earth-trained brain finds almost impossible to grasp. On Earth, even in what you consider a vacuum, there are still billions of molecules per cubic centimetre. The best laboratory vacuums humans have created on Earth still contain tens of thousands of molecules in that same tiny space. But out here, in the interplanetary medium, you're looking at roughly 5 to 10 particles per cubic centimetre. Not billion, not million, 5 to 10. Mostly protons and electrons from the solar wind, the sun's constant exhalation of charged particles, along with a scattering of lonely hydrogen atoms that drift through the void like dandelion seeds in an abandoned field. This is what makes the temperature question so strange out here. Remember, temperature is the average kinetic energy of particles. These few particles floating past you actually do have kinetic energy. These solar wind particles are moving quite fast, some of them at several hundred kilometers per second, which means they have a high temperature in the strict physics sense. If you could somehow measure the average speed of just these particles, you would get a number corresponding to perhaps 100,000 degrees Celsius or more. That sounds terrifying until you remember that there are only 5 of them per cubic centimetre. Their collective ability to transfer heat to you or anything else is essentially zero. It is the difference between being hit by 5 tiny grains of sand moving at rifle speed and being hit by a tsunami. The individual particles are energetic, but there are so few of them that their total thermal energy is negligible. This is one of the most important distinctions in all of thermal physics, and it trips people up constantly. The difference between temperature and heat. Temperature is the average energy per particle. Heat is the total energy in a system. A thimble of water at 90 degrees Celsius has a higher temperature than a bathtub of water at 40 degrees, but the bathtub contains far more total thermal energy. If you fell into the bathtub, it could warm you for hours. If you spilled the thimble on your hand, you would flinch and then move on with your life. Out here in the interplanetary void, you're essentially surrounded by a vast, near-infinite bathtub that contains almost no water. The temperature of those rare particles might be impressive on paper, but the actual heat available to affect you is almost nothing. Here is a historical fact that helps anchor this. The concept of distinguishing between heat and temperature was formalised in the 18th century, primarily through the work of Scottish chemist Joseph Black. Before Black, most people used the two terms interchangeably, which is like confusing speed with distance. Black introduced the concept of specific heat capacity, the idea that different substances required different amounts of energy to raise their temperature by the same amount. Water, for example, requires far more energy per degree than iron does, which is why a pot heats up faster than the water inside it. Black also developed the concept of latent heat, the energy absorbed or released during phase changes like melting or boiling without any change in temperature. His lectures in Edinburgh in the 1760s were wildly popular, drawing students who would go on to reshape chemistry and physics. Historians still argue whether Black deserves more credit than he typically receives for laying the groundwork of thermodynamics, or whether his contributions have been fairly acknowledged alongside Carnot, Clausius and Kelvin. And here is a quirky detail that deserves a quiet smile. Joseph Black was so meticulous in his experiments that he reportedly kept his laboratory at a constant temperature by monitoring it obsessively, refusing to let anyone open windows or doors during measurements. His students described him as gentle, softly spoken, and extraordinarily precise, a man who seemed to embody the calm, controlled energy he spent his career studying. He died peacefully in 1799, sitting in his chair with a bowl of milk balanced perfectly on his knee, not a drop spilled. It is perhaps the most on-brand death in the history of science. So here you float, in this near-perfect vacuum between worlds, and the rules of temperature begin to unravel in ways that feel almost philosophical. If you placed a thermometer out here, what would it read? The answer depends entirely on its surroundings. If the thermometer is in direct sunlight, it will absorb solar radiation and warm up, potentially reaching over 100 degrees Celsius depending on its surface properties. If you rotate it into shadow, shielded from the sun, it will begin radiating away its own heat with nothing to replace it, and its temperature will plummet, eventually approaching the baseline hum of the universe itself. The thermometer is not measuring the temperature of space, it is measuring its own temperature, which is determined by the balance between the radiation it absorbs and the radiation it emits. Space itself does not have a temperature in any meaningful everyday sense. It is a stage, not a performer. You drift a little, weightless and thoughtful. A tiny micrometeorite, no bigger than a grain of sand, zips past you at 40 kilometers per second. A blink and you miss it reminder that the void is not perfectly empty, just very nearly so. Somewhere behind you, the earth glows blue and white. Ahead, the moon hangs grey and patient. And between them, there is almost nothing at all, just a handful of particles per cubic centimetre and an ocean of silent photons passing through on their way to somewhere else. You stay floating in that vast quiet for a moment longer, letting the emptiness settle around you like a blanket made of nothing. But the void is not entirely without a voice. There is a whisper out here, so faint and so ancient that detecting it required some of the most sensitive instruments humanity has ever built. It comes from every direction simultaneously. It has no single source, no point of origin you can aim a telescope at and say there. That is where it started. It is everywhere, filling every cubic centimetre of the observable universe, and it has been travelling for over 13 billion years. It is the cosmic microwave background, and it is, in a very real sense, the temperature of space itself. To understand what it is, you need to rewind. Not a few centuries, not a few millennia, but almost all the way back to the beginning of everything. About 13.8 billion years ago, the universe was unimaginably hot and dense, a seething plasma of particles and radiation so tightly packed that light could not travel freely. Photons were constantly absorbed and re-emitted by charged particles, trapped in a fog of primordial matter. The universe was opaque, like trying to see through a wall of fire. Then, roughly 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. This event, called recombination, which is a mildly misleading name since the electrons and protons had never been combined before, suddenly freed the photons. The fog lifted. Light could travel in straight lines for the first time, and the universe became transparent. Those newly liberated photons have been streaming through space ever since, cooling and stretching as the universe expands, and they are what we detect today as the cosmic microwave background. When those photons were first released, the universe had a temperature of about 3000 Kelvin, glowing a soft orange-red, roughly the colour of a cooling ember. But over 13 billion years of cosmic expansion, the wavelengths of those photons have been stretched enormously, shifting from visible light down into the microwave part of the electromagnetic spectrum. The temperature associated with this radiation has dropped to about 2.7 Kelvin, which is 2.7 degrees above absolute zero, or roughly minus 270 degrees Celsius. This is the faint hum that fills all of space. It is the afterglow of the Big Bang, the oldest light in existence, and it sets the effective temperature floor of the cosmos. No matter where you go in the universe, no matter how far from any star or galaxy, you will always be bathed in this feeble radiation, and if you sit long enough with no other energy source, you will eventually cool down to 2.7 Kelvin and no further. The discovery of the cosmic microwave background is one of the great stories of accidental science. In 1965, two radio astronomers at Bell Telephone Laboratories in New Jersey, Arne Penzias and Robert Wilson, were working with a large horn antenna originally designed for satellite communication. They kept picking up a persistent low-level noise that they could not eliminate. They pointed the antenna at New York City, thinking urban radio interference might be the culprit. Nothing changed. They pointed it at the sky in every direction. Same noise. They even climbed inside the antenna and cleaned out pigeon droppings, suspecting that bird waste might be causing a signal. The pigeons, it should be noted, kept coming back, apparently quite fond of the antenna's cosy interior. Penzias and Wilson eventually contacted Robert Dicke at Princeton, who had been independently predicting that such a background radiation should exist. When Dicke heard the news, he reportedly turned to his colleagues and said something along the lines of, "Well boys, we have been scooped." Penzias and Wilson won the Nobel Prize in 1978 for what is essentially the most consequential pigeon-related discovery in history. Historians still argue whether Penzias and Wilson fully appreciated the cosmological significance of their finding at the moment of discovery, or whether they initially viewed it as an engineering nuisance that happened to have scientific implications. The truth is probably somewhere in between, as it usually is when human beings stumble onto something enormous while trying to do something mundane. And here is a quirky detail that adds a layer of wonder. The cosmic microwave background is not perfectly uniform. It has tiny fluctuations, variations of about 1 part in 100,000, which represent slight differences in density in the early universe. These minuscule ripples are the seeds from which all structure in the cosmos eventually grew. The galaxies, the clusters of galaxies, the vast cosmic web of filaments and voids that makes up the large-scale structure of the universe, all of it traces back to those barely perceptible temperature variations in the afterglow of creation. The difference between a region that would become a supercluster of galaxies and a region that would become an empty void was, at the time of recombination, a temperature variation smaller than the difference you would notice between one sip of tea and the next. The universe built everything you see from almost nothing at all. So when someone asks what the temperature of space is, the most honest answer is about 2.7 Kelvin, the temperature of the cosmic microwave background. This is the bath of radiation that fills the universe, the baseline warmth left over from the moment the cosmos became transparent. It is incredibly cold by human standards, cold enough to freeze every liquid you have ever encountered almost instantly, cold enough to make liquid nitrogen look balmy by comparison. But it is not zero. It is not nothing. It is a whisper, a faint thermal memory of a time when the entire universe was a blazing inferno, and it has been cooling ever since, slowly and patiently for longer than the Earth, the Sun, or the Milky Way have existed. You float there, surrounded by this ancient hum, photons that have been travelling since before there were stars to interrupt their journey. And you realise that when we say space is cold, we are really saying that the universe has been cooling down for a very, very long time, and this is where it currently sits on that long, slow slide towards stillness. You pull yourself back from that ancient hum and turn your attention to something more immediate, more human. You're still floating in space, after all, and the practical question nudges its way forward. What would actually happen to you out here? Not the philosophical you, not the shrunken molecule-sized you, but the real, flesh and blood, currently breathing you. If you stepped outside a spacecraft with no protection, would you freeze instantly, the way science fiction movies love to suggest? Would you turn into a human popsicle, drifting through the void like a grim novelty item? The answer, perhaps surprisingly, is no, not even close. In fact, the more immediate problem is the opposite one entirely. You would overheat. This sounds absurd given everything we have discussed about the emptiness and coldness of space, but it makes perfect sense once you remember the 3 methods of heat transfer from our campfire conversation. Your body generates heat constantly. Every metabolic process, every muscle contraction, every thought flickering through your brain produces thermal energy as a byproduct. On Earth, you shed this excess heat effortlessly. The air around you carries it away through conduction and convection. You sweat, and the evaporation of moisture from your skin pulls heat with it. You barely think about any of this because your body has been managing its thermal budget since before you were born. But in space, 2 of your 3 cooling methods vanish instantly. There's no air to conduct heat away from your skin. There is no fluid to carry warmth through convection. The only remaining option is radiation, and while your body does radiate infrared energy, it does so slowly, far too slowly to keep up with the heat your metabolism generates. Without a way to dump that excess warmth, your core temperature would begin to rise. This is precisely the problem that spacecraft and spacesuit engineers have been wrestling with since the dawn of human spaceflight. When NASA was designing suits for the Apollo missions in the 1960s, the primary thermal challenge was not keeping astronauts warm on the lunar surface, it was keeping them cool. The suits used a system of water-cooled undergarments, essentially a network of thin tubes woven into a fabric layer worn against the skin, through which chilled water circulated to absorb body heat. That heat was then carried to a sublimator, a device that expelled water into the vacuum of space, where it would instantly sublime from liquid to vapour, carrying thermal energy away in the process. It was elegant, effective, and frankly, a little bit funny. Humans walked on the moon kept alive partly by a system that worked on the same principle as sweating, just with fancier plumbing. Here is the historical fact for this stretch. During the Gemini program in the mid-1960s, which preceded Apollo and tested many of the technologies needed for a moon landing, astronaut Eugene Cernan performed a spacewalk during the Gemini 9A mission in 1966 that nearly ended in disaster. His spacesuit's cooling system could not keep up with the exertion of moving in microgravity, and his visor fogged up so badly from perspiration that he could barely see. His heart rate spiked dangerously, and he was essentially baking inside his own suit. He made it back inside the capsule, but the experience was harrowing. Historians still argue whether the near failure of Cernan's spacewalk was primarily a suit design problem or a training problem. since the physical demands of working in a pressurized suit in zero gravity had been drastically underestimated. Either way, the incident reshaped how NASA approached thermal management in all subsequent missions. And here is a quirky tidbit that deserves its own quiet moment of appreciation. The International Space Station, that enormous laboratory orbiting roughly 400 kilometers above your head, generates so much excess heat from its electronics, experiments, and human occupants that it requires a massive external cooling system to survive. The station uses ammonia as a coolant, pumping it through enormous radiator panels that extend outward like wings. These radiators work by emitting infrared radiation into space, the only viable cooling method in a vacuum, and they are surprisingly large. If you have ever seen photographs of the station and noticed those flat white panels extending from the main truss structure, those are not solar panels. The solar panels are the golden brown ones. The white panels are radiators, quietly dumping excess heat into the void so that the astronauts inside do not slowly cook. The station produces enough waste heat to warm several houses, and all of it has to be radiated away into an environment that cannot carry it off by any other means. Now, this does not mean that cold is never a problem in space. It absolutely is, just not in the way movies depict. The issue arises when you move into shadow. Remember the thermometer from a couple of sections ago, the one whose reading depended entirely on whether it was in sunlight or shade. The same applies to spacecraft and suits. In direct sunlight in low Earth orbit, surfaces can reach over 120 degrees Celsius, rotate into Earth's shadow, and those same surfaces can plunge to minus 150 degrees or lower within minutes. This is an astonishing thermal swing, and managing it is one of the great unsung challenges of space engineering. The station's orbit takes it through roughly 16 sunrises and sunsets every 24 hours, which means its exterior is constantly cycling between roasting and freezing. The multi-layer insulation blankets that cover much of the station's surface are designed to moderate these swings, acting like a thermos bottle that slows both heating and cooling. So here you are floating in the void, and the truth is more nuanced than you expected. Space is not simply cold, it is thermally extreme in both directions, and the real danger is not freezing or boiling, but managing the balance between the two. Your body, your spacecraft, your suit, everything is simultaneously gaining energy from the sun and losing energy through radiation, and survival depends on keeping those two processes in equilibrium. It is a tightrope walk performed at 7.7 kilometers per second, which is roughly the orbital velocity of the station, and the engineers who make it work deserve far more appreciation than they typically receive. You picture yourself back inside a spacecraft, pulling off the helmet, feeling the carefully controlled 72-degree air against your face, and you think about how much invisible work goes into making that ordinary sensation possible out here, where nothing is ordinary at all. You drift back toward the Earth now, not all the way down to that warm patch of July grass, but just close enough to graze the upper edges of the atmosphere. And here is where things get layered, literally. The Earth is wrapped in a series of gaseous shells, each one with its own personality, its own thermal quirks, its own way of interacting with the energy streaming in from the sun. Together, these layers form the atmosphere, a word that comes from the Greek atmos, meaning vapour, and sphaira, meaning sphere. A sphere of vapour. It sounds almost fragile when you say it like that, and in cosmic terms it is. If you shrank the Earth to the size of a basketball, the atmosphere would be thinner than a coat of paint. Yet this impossibly thin skin of gas is the reason you exist, the reason oceans are liquid, the reason the surface of the planet is not a radiation-blasted wasteland swinging between the thermal extremes you just experienced in orbit. You enter the troposphere first, the lowest layer, the one you actually live in. It extends from the surface up to about 12 kilometers at the equator. though it is a bit shallower at the poles because even the atmosphere cannot resist being slightly squished by the Earth's rotation. The troposphere contains roughly 80% of the atmosphere's total mass and virtually all of its weather. This is where clouds form, where rain falls, where winds howl and breezes whisper. Temperature here decreases with altitude, dropping about 6.5 degrees Celsius for every 1,000 meters you climb, which is why mountaintops are cold and airplanes fly through freezing conditions even on a summer day. The reason for this cooling is straightforward. The sun does not heat the troposphere from the top down. It heats the ground first, and the ground then warms the air above it through conduction and convection. Those two heat transfer methods that work perfectly well when you have molecules to play with. The higher you go, the farther you are from that warm surface, and the cooler the air becomes. Then you hit the tropopause, a thin boundary layer where the temperature stops dropping and briefly holds steady, like a musical rest between movements. Above it lies the stratosphere, extending up to about 50 kilometers. Here, something unexpected happens. The temperature starts rising again. You're moving away from the Earth's surface, further from the source of warmth, and yet the air is getting hotter. The culprit is ozone. The stratosphere contains the ozone layer, a region rich in O3 molecules that absorb ultraviolet radiation from the sun with remarkable efficiency. This absorption converts UV energy into heat, warming the stratosphere from within. It is a neatly self-contained heating system, and it is also the reason the ozone layer is so critical to life on the surface. By absorbing that ultraviolet radiation up here, it prevents it from reaching down there, where it would cause rampant skin cancer, cataracts, and damage to plant life. The ozone layer is essentially a chemical bodyguard, quietly intercepting harmful energy and converting it to warmth at an altitude where it bothers no one. Above the stratosphere, you pass through the stratopause and enter the mesosphere, which extends up to about 85 kilometers and is, frankly, the neglected middle child of atmospheric layers. The temperature drops again here, plunging to as low as minus 90 degrees Celsius near its upper boundary, making the mesopause the coldest part of Earth's entire atmosphere. Colder than Antarctica, colder than the poles in winter, colder, in fact, than many places in the inner solar system that you might expect to be far more frigid. The mesosphere is where most meteors burn up upon entry, which means it is essentially Earth's meteor shield, and yet it gets almost no attention in popular science. Historians still argue whether the mesosphere has been historically neglected in research, because it is too high for weather balloons and too low for satellites, making it notoriously difficult to study, or whether it simply lacks the dramatic appeal of the layers above and below it. The mesosphere is the atmospheric equivalent of a reliable co-worker who never gets promoted. And here is a quirky detail worth savouring. In the mesosphere, during polar summers, something eerie happens. Tiny ice crystals form at the very top of the layer, creating noctilucent clouds, the highest clouds on Earth, shimmering at altitudes around 80 kilometers. They are visible only around twilight, when the sun has set for observers on the ground, but still illuminates these impossibly high wisps from below the horizon. They glow a ghostly blue-white against the darkening sky, and they were first reported in 1885, 2 years after the massive eruption of Krakatoa, leading some researchers to initially suspect volcanic dust was responsible. Modern science suggests they are primarily composed of water ice nucleating on meteoric dust particles, which means you're looking at clouds made of space debris and frozen breath at the edge of the atmosphere. They are one of the most beautiful and least known phenomena the sky has to offer. Above the mesosphere lies the thermosphere, which we will visit properly very soon because it contains one of the most brain-bending thermal paradoxes you will encounter tonight. And above even that sits the exosphere, the outermost whisper of the atmosphere, where individual molecules arc on ballistic trajectories like tiny satellites, some of them escaping Earth's gravity entirely and drifting off into space. The exosphere has no clear upper boundary. It simply fades, particle by particle, into the interplanetary void, a gradual dissolution of atmosphere into emptiness that feels poetic if you sit with it long enough. But the real magic of the atmosphere, the reason we're here, is not in any single layer. It is in the collective effect. All of these layers working together form a system that intercepts solar energy, distributes it, traps just enough of it, and reflects the rest back into space. Without this system, the average surface temperature of the Earth would be roughly minus 18 degrees Celsius, well below freezing, and the oceans would be ice. With it, the average sits around a comfortable 15 degrees Celsius, a difference of 33 degrees that makes the distinction between a frozen, lifeless rock and a world teeming with forests and fish, and people listening to sleepy science stories in bed. You float at the edge of this invisible blanket, looking down at the swirl of clouds and the dark blue of oceans beneath them, and you understand that the atmosphere is not just air. It is a thermal machine, an energy manager, a negotiator between the fury of the sun and the frigid void of space. That 33-degree difference you just encountered, the gap between a frozen wasteland and a living world, has a name. You have heard it many times, almost certainly in a context that made it sound like a villain. But the greenhouse effect was a hero long before it became a headline, and understanding its original role is essential to understanding why the Earth is warm, why Venus is an inferno, and why the whole relationship between stars and planets and atmospheres is more delicate than you might think. The basic mechanism is disarmingly simple. Sunlight arrives at the Earth in the form of short-wavelength radiation, primarily visible light and ultraviolet. The atmosphere is mostly transparent to these wavelengths, so they pass through and strike the surface. The ground, the oceans, the rooftops, the parking lots, everything absorbs this energy and warms up. But here is the crucial twist. When these surfaces re-emit energy, they do so at longer wavelengths, primarily infrared. And the atmosphere is not transparent to infrared. Certain gases, carbon dioxide, water vapor, methane, nitrous oxide, and a handful of others, are very good at absorbing infrared radiation. They catch that outgoing energy, absorb it, and re-emit it in all directions, including back down toward the surface. This creates a thermal loop. Energy comes in as visible light, gets converted to infrared, and then bounces around between the surface and the atmosphere instead of escaping cleanly into space. The surface stays warmer than it would otherwise be. That is the greenhouse effect, and without it, you would not be here. The name itself is a bit misleading. An actual greenhouse stays warm primarily because it physically traps warm air inside, preventing convection from carrying heat away. The atmospheric greenhouse effect works through a different mechanism entirely, the absorption and re-emission of radiation. But the name stuck after it was coined in the 19th century, and at this point, trying to change it would be like trying to rename a beloved pet. The pet does not care, and everyone is already used to the old name. The scientist most commonly credited with first describing the greenhouse effect is Joseph Fourier, the French mathematician and physicist who is also famous for Fourier transforms, a mathematical tool so fundamental that it shows up everywhere from music production to medical imaging. In the 1820s, Fourier calculated that the Earth should be significantly colder than it actually is, given its distance from the Sun, and proposed that the atmosphere must be doing something to retain heat. He compared it, somewhat loosely, to a glass vessel that lets light in but traps warmth. He didn't fully work out the mechanism, but he identified the puzzle. A few decades later, in 1856, an American scientist named Eunice Newton Foote conducted experiments showing that carbon dioxide and water vapor trapped more heat than other gases when exposed to sunlight. Her work was presented at a scientific conference by a male colleague, because the conventions of the era did not permit her to present it herself. Historians still argue whether Foote has been unfairly overshadowed by John Tyndall, the Irish physicist who published more detailed and rigorous experiments on the heat-absorbing properties of gases in 1859, 3 years after Foote's work. Tyndall is often credited as the father of the greenhouse effect, but Foote got there first, with less equipment and less recognition, which is a pattern depressingly familiar in the history of women in science. And here is the quirky tidbit that makes this story even richer. Svante Arrhenius, the Swedish chemist who won the Nobel Prize in 1903 for his work on electrolytic dissociation, was the first to calculate how changes in atmospheric carbon dioxide levels could affect the Earth's surface temperature. In 1896, he spent months performing thousands of tedious calculations by hand, estimating that doubling the concentration of carbon dioxide would raise global temperatures by about 5 to 6 degrees Celsius. He was remarkably close to modern estimates. But here is the funny part. Arrhenius did not view this as a threat. Living in chilly Sweden, he thought a warmer world sounded rather pleasant, and predicted that increased coal burning might eventually create a more comfortable climate for humanity. He imagined future generations enjoying balmier Scandinavian winters and longer growing seasons. One can only wonder what he would make of the current conversation. Now the greenhouse effect in its natural, unenhanced state is a marvel of planetary engineering. It keeps the Earth warm enough for liquid water, which is the prerequisite for every form of life we know about. It moderates temperature swings between day and night. It creates the conditions for a hydrological cycle, for weather, for the slow geological processes that recycle carbon and regulate the atmosphere over millions of years. It is, by any reasonable measure, one of the most important phenomena in the solar system for the existence of biology. But it has a dark side, and the dark side is visible every time you look at Venus. Venus is almost the same size as Earth. It sits only slightly closer to the Sun, receiving about twice the solar energy per square meter. If it had an atmosphere like Earth's, its surface temperature might be a few tens of degrees warmer. Uncomfortable perhaps, but not lethal. Instead, Venus has a surface temperature of roughly 460 degrees Celsius, hotter than Mercury, which is far closer to the Sun. The reason is a greenhouse effect that has gone catastrophically wrong. Venus's atmosphere is about 96% carbon dioxide, and it is thick, roughly 90 times the surface pressure of Earth's atmosphere. The infrared trapping is so efficient that virtually no thermal energy escapes. The planet is wrapped in a suffocating thermal blanket that has been thickening over billions of years in a process called the Runaway greenhouse effect. Whatever oceans Venus may once have had, and some models suggest it might have had oceans for billions of years, have long since boiled away, their water vapour broken apart by ultraviolet light and the hydrogen lost to space. Venus is what happens when the greenhouse effect has no check, no regulation, no off switch. You look down at the Earth from your perch at the edge of the atmosphere, and you feel a new appreciation for the thinness of the margin. Too little greenhouse effect and you get a frozen ball of ice. Too much and you get a pressure cooker with sulfuric acid clouds. Earth sits in the narrow window between those extremes, held there by a combination of carbon dioxide, water vapour, geological recycling, and what some scientists call sheer planetary luck. The Sun provides the energy, the atmosphere decides how much to keep, and the balance, for now, holds. You turn away from Venus and its cautionary tale and look instead toward the Moon, hanging there in the sky like a pale, pockmarked lantern. The Moon has no atmosphere to speak of. A few stray atoms of sodium, potassium and argon cling to its surface in what scientists generously call an exosphere, but it is so thin that it might as well not exist. There is no greenhouse effect, no convective mixing, no ozone layer, no weather. The moon is naked rock, fully exposed to whatever the universe throws at it, and what the universe throws at it, thermally speaking, is extreme. Stand on the lunar surface at the subsolar point, the spot where the sun is directly overhead, and the ground beneath your boots reaches about 127 degrees Celsius. That is hotter than boiling water. Hotter than any naturally occurring temperature on Earth's surface outside of volcanic vents. The regolith, that fine powdery soil that covers the moon, absorbs solar radiation greedily because there is no atmosphere to filter or scatter the incoming light. Every photon that arrives hits the ground unimpeded and deposits its energy directly. Now take 3 steps into the shadow of a boulder. Not 100 meters, not a kilometer, just a few paces into shade. The temperature drops like a stone thrown off a cliff. In permanent shadow, such as the floors of deep craters near the lunar poles, temperatures plunge to minus 230 degrees Celsius or lower. That is colder than the surface of Pluto, colder than liquid nitrogen, approaching the cosmic microwave background temperature you met a few sections ago. This staggering swing over 350 degrees between sunlight and shadow happens because there is no medium to distribute heat. On Earth, when one side of a building is in shade, the air carries warmth around from the sunny side, moderating the difference. Wind, convection, humidity, all of these conspire to blur the thermal boundary between light and dark. On the moon, there is nothing. The boundary between scorching and freezing is as sharp as the shadow itself. 1 centimeter in sunlight broiling, 1 centimeter in shade plunging toward the abyss. It is a thermal cliff edge, and it exists because radiation is the only game in town when there is no atmosphere to soften the rules. The same principle applies to the International Space Station, which you visited not long ago when we were talking about astronauts overheating. The station orbits at roughly 400 kilometers above the Earth, completing 1 full orbit every 90 minutes. This means it passes from full sunlight into Earth's shadow and back again about 16 times every 24 hours. Each transition is a thermal shock. Surfaces facing the sun heat up rapidly, while surfaces in shadow cool just as fast. The temperature difference between the sunlit and shadowed sides of the station can exceed 200 degrees Celsius, which is the kind of thermal stress that would tear most everyday materials apart. Engineers manage this with multi-layer insulation, those shiny gold and silver blankets you see in photographs of spacecraft, which work by reflecting radiation and reducing the rate of both heating and cooling. Each layer is separated by a vacuum gap, minimizing conduction between layers, and the whole assembly acts like a thermos bottle wrapped around the station's vital components. Here is a historical fact that grounds this beautifully. During the Apollo 13 mission in 1970, the crew famously lost most of their electrical power after an oxygen tank exploded in the service module. Among the many cascading crises they faced was a thermal one. With the spacecraft powered down to conserve energy, the cabin temperature dropped to near freezing. Water condensed on the walls and instrument panels. The astronauts shivered in their sleeping bags, breathing clouds of visible vapor. Yet at the same time, certain parts of the spacecraft's exterior were baking in direct sunlight. The mission became an unplanned demonstration of exactly how unforgiving the thermal environment of space is when your carefully engineered systems fail. Historians still argue whether the crew's survival was more attributable to the ingenuity of the ground-based engineers who improvise solutions in real time or to the astronauts' own calm under pressure. The consensus, if there is one, seems to be that it required both in equal measure. And here is a quirky tidbit that quietly changes the way you think about the moon. Those permanently shadowed craters near the lunar poles, the ones where temperatures hover around minus 230 degrees, are not just cold. They are ancient cold traps. Because sunlight has not touched their floors in billions of years, any volatile substance that wandered in, water vapour from comet impacts for instance, would have frozen solid and stayed frozen, accumulating over geological time. In 2009, NASA's LCROSS mission deliberately crashed a spent rocket stage into one of these craters, Coldest, near the South Pole, and analysed the debris plume. They found water ice along with traces of mercury, silver, carbon dioxide, ammonia, and several other compounds. The Moon, that bone-dry, lifeless rock, has ice hiding in its coldest shadows, preserved by the same absence of atmosphere that makes its thermal swings so violent. Some of that ice may be billions of years old, delivered by comets that struck the Moon when life on Earth was still single-celled. It is a time capsule written in frost. You stand in your imagination at the rim of one of these craters, looking down into a darkness so complete that not a single photon of sunlight has touched the floor in longer than complex life has existed on Earth. The cold down there is almost incomprehensible, a cold born not from wind or weather but from simple, absolute deprivation. No energy in, no warmth possible, just rock and ice and silence, sitting at a temperature that would make the void between the stars feel like a warm bath by comparison. And you realise that shadows in space are not like shadows on Earth. On Earth, a shadow is a slightly cooler patch of ground where you rest on a hot day. In space, a shadow is a boundary between two entirely different thermal realities, separated by nothing more than the angle between you and the nearest star. You rise from the Moon's cratered rim and float upward again, back through the layers of Earth's atmosphere, but this time you're not heading for the troposphere or the stratosphere. You're going higher, much higher, into a region that's about to tie your brain into a gentle, sleepy knot. You're entering the thermosphere, that layer beginning at roughly 85 kilometers above the surface and extending to somewhere between 500 and 1,000 kilometers, depending on solar activity. And the thermosphere has a secret that sounds like it was designed specifically to confuse undergraduate physics students and anyone trying to sleep while listening to a science podcast. The particles up here are hot, staggeringly hot. Individual molecules of oxygen and nitrogen in the thermosphere can have temperatures exceeding 2000 degrees Celsius. Some measurements during periods of intense solar activity have recorded particle temperatures above 2,500 degrees. By any standard definition of temperature, this is ferociously hot. It is hotter than the melting point of steel, hotter than lava, hotter in fact than the surface of some cooler stars. And yet if you floated up here without a spacesuit, you would not burn, you would freeze. A thermometer placed in the thermosphere would read well below zero. Your skin would feel cold, assuming you were still capable of feeling anything at all in the near vacuum, which you would not be. But let us maintain the thought experiment for the sake of understanding. How can something be 2,000 degrees and freezing at the same time? The answer is the distinction between temperature and heat that we explored a few sections ago when you were floating between the Earth and the Moon, and it is worth revisiting now because the thermosphere is the most dramatic illustration of this difference anywhere in our planet's vicinity. Remember, temperature is the average kinetic energy per particle. The molecules in the thermosphere are moving extraordinarily fast because they absorb extreme ultraviolet radiation and X-rays from the sun directly, without any lower atmosphere to filter those energies out. Each individual molecule is rocketing along at tremendous speed, and speed is what temperature measures. But there are almost no molecules up here. The density in the thermosphere is vanishingly low, millions of times less dense than the air you're breathing right now. If you scooped up a cubic meter of thermospheric gas, you would have a pitiful number of particles. Each one is blazing with kinetic energy, but collectively they carry almost no thermal energy at all. They are too few and too far apart to transfer any meaningful heat to an object placed among them. Think of it this way. Imagine a single mosquito flying at the speed of a bullet. That mosquito has an extremely high kinetic energy for its size. Its temperature, in the physics sense, is enormous. But if it hits you, you will barely notice because its mass is negligible. Now imagine a bathtub full of warm water at a comfortable 40 degrees. Each water molecule is moving far more slowly than the bullet-speed mosquito, but there are so many molecules, trillions upon trillions, that the total thermal energy is enough to warm your entire body for a long soak. The thermosphere is the mosquito. The troposphere is the bathtub. Temperature tells you about the individual particle. Heat tells you about the crowd. This paradox confused early atmospheric scientists considerably. When the first sounding rockets reached thermospheric altitudes in the late 1940s and 1950s, the data coming back seemed contradictory. Instruments designed to measure particle energy were returning scorching numbers, while instruments designed to measure bulk thermal effects were registering almost nothing. It took careful theoretical work to reconcile these findings and establish clearly that temperature and heat are not the same thing, a lesson the thermosphere teaches more vividly than any classroom ever could. Here is a historical fact that anchors this era. Much of the early research into the upper atmosphere was driven not by pure scientific curiosity, but by military necessity. After World War II, captured German V-2 rockets were repurposed by American scientists to carry instruments to altitudes never before reached. The Army's White Sands Proving Ground in New Mexico became a launch pad for scientific discovery almost by accident. Researchers would bolt instruments onto rockets originally designed to devastate cities and fire them straight up, collecting a few minutes of data before the rocket arced back down and slammed into the desert. Historians still argue whether the rapid pace of upper atmosphere research in the late 1940s and 1950s would have been possible without the Cold War military infrastructure that funded it, or whether civilian science would have eventually reached the same altitudes through slower, more deliberate means. The uncomfortable truth is that war has often been the most effective accelerator of scientific progress, a fact that sits uneasily alongside the human cost. And here is a quirky detail that gives the thermosphere another layer of personality. The International Space Station orbits within the thermosphere. Yes, the station that you toured earlier, with its ammonia cooling loops and its astronauts managing their body heat, flies through a region where individual air molecules are hotter than molten iron. The astronauts are completely unaffected by this, because the density is so low that the rate of energy transfer from these particles to the station's hull is negligible. The station does experience a tiny amount of atmospheric drag up here, enough that it needs periodic reboost to maintain its orbit, but the thermal effect of those superheated molecules is essentially nil. You could wave your hand through 2000 degree gas and feel nothing, because there is simply not enough of it to matter. It is the most counterintuitive sauna in the solar system. The thermosphere also expands and contracts dramatically with solar activity. During solar maximum, when the sun is throwing out more ultraviolet and X-ray radiation, the thermosphere heats up and puffs outward, sometimes increasing the drag on satellites enough to alter their orbits. During solar minimum, it contracts and cools, relatively speaking. This breathing pattern means the boundary between the thermosphere and the exosphere above it is not fixed but fluctuates over the 11-year solar cycle. The atmosphere itself is alive, responding to the sun's moods like a restless sleeper shifting beneath a blanket. You float there among these blazing lonely molecules, each one a tiny furnace lost in an ocean of nothing, and you appreciate for the first time just how slippery the concept of hot and cold really is. You pull yourself away from the thermosphere's paradox and decide it is time to go planet hopping, After all, the relationship between the sun's heat and the cold of space does not play out the same way on every world. Each planet in the solar system has its own answer to the question of how to handle the energy the sun sends its way, and those answers depend on a surprisingly short list of factors: distance from the sun, size, composition, and whether or not the planet bothered to hold onto an atmosphere. That last one turns out to be the most important variable of all, as you have probably started to suspect. You begin with Mercury, the closest planet to the sun, orbiting at an average distance of about 58 million kilometers. Mercury is small, barely larger than the Moon, and it has essentially no atmosphere. A whisper of sodium, a trace of oxygen, nothing that would register on any meaningful scale. This means Mercury is, thermally speaking, in almost the same situation as the Moon. Direct sunlight hits the surface with no filter, no buffer, no redistribution. The dayside surface temperature climbs to roughly 430 degrees Celsius, hot enough to melt lead, hot enough to melt zinc, hot enough to make you reconsider every complaint you have ever made about summer. But the night side, the hemisphere facing away from the sun, drops to about minus 180 degrees Celsius, a swing of over 600 degrees between one side of the planet and the other. And here is the thing that makes Mercury even stranger. Because of a peculiar gravitational resonance with the sun, Mercury rotates very slowly, completing just 3 rotations for every 2 orbits. A single solar day on Mercury, from one sunrise to the next, lasts about 176 Earth days. This means the dayside has nearly 3 months of continuous, unrelenting solar bombardment before the surface finally rotates into shadow and begins to cool. The ground bakes for so long that heat penetrates deep into the regolith, and when night finally arrives, it takes equally long to radiate all that energy away. Mercury is a planet of extremes, governed entirely by radiation, with no atmospheric blanket to soften any edge. Now hop outward, past Venus and Earth, which you have already visited, and land on Mars. Mars sits about 228 million kilometers from the Sun, roughly 1.5 times the Earth's distance. It receives only about 43% of the solar energy per square meter that Earth does. But distance alone does not explain why Mars is so cold. The real culprit, once again, is atmosphere. Mars has one, technically, but it is painfully thin. The surface pressure on Mars is less than 1% of Earth's, about 600 pascals compared to Earth's 101,000. It is mostly carbon dioxide, which should create a greenhouse effect, and it does, but the atmosphere is simply too thin to trap much heat. The greenhouse warming on Mars amounts to roughly 5 degrees Celsius, a pitiful contribution compared to Earth's 33 degrees. The result is an average surface temperature of about minus 60 degrees Celsius, with extremes ranging from a relatively mild 20 degrees at the equator during summer to minus 140 at the poles in winter. Here is a historical fact that connects to the Martian cold. In the late 19th century, the Italian astronomer Giovanni Schiaparelli observed linear features on Mars that he called canali, the Italian word for channels. The term was mistranslated into English as canals, implying artificial construction, and this sparked a global frenzy of speculation about Martian civilizations. The American astronomer Percival Lowell became the most vocal champion of the idea, building an entire observatory in Flagstaff, Arizona, dedicated in part to studying Mars. Lowell published detailed maps showing networks of canals that he believed were irrigation systems built by an intelligent Martian civilization struggling to distribute water on a drying planet. Historians still argue whether Lowell was a visionary who popularized planetary science and inspired generations of astronomers, or a wealthy amateur who let his imagination override his data and set back serious Mars research by decades. The canals, of course, turned out to be optical illusions, and Mars turned out to be far colder, drier, and more inhospitable than Lowell ever imagined. And here is a quirky detail about Martian cold that feels almost whimsical. At the polar ice caps of Mars, it gets cold enough for carbon dioxide itself to freeze out of the atmosphere. Dry ice. The stuff you might associate with Halloween fog machines and theatrical special effects forms naturally on Mars as frost and snowfall. During Martian winter, carbon dioxide snow falls from thin clouds onto the polar regions, building up seasonal ice caps that advance and retreat with the seasons. The Phoenix lander, which touched down near the Martian North Pole in 2008, observed this carbon dioxide frost firsthand, watching it appear on the surface as temperatures dropped. An entire world where the air itself freezes and falls as snow. It is the kind of detail that makes Mars feel less like a dead rock and more like a strange, cold cousin of Earth, playing by the same physical rules but with vastly different parameters. The comparison between these worlds makes the pattern unmistakable. Mercury, with no atmosphere, experiences the full unmoderated fury of proximity to the Sun on one side, and the full unmoderated emptiness of space on the other. Mars, with a thin atmosphere, gets a tiny thermal cushion that barely registers. Earth, with a substantial atmosphere and an active greenhouse effect, maintains a narrow, life-friendly temperature band. Venus, with a massive carbon dioxide-choked atmosphere, has trapped so much heat that its surface could melt electronics. The Sun sends energy outward impartially, without preference or direction. What each planet does with that energy depends almost entirely on the gaseous envelope it has managed to hold on to. The atmosphere is the negotiator, the translator, the middleman between stellar fire and cosmic cold. Without it, you are Mercury. With too much, you are Venus. This sweet spot is achingly narrow. You sit with that thought for a moment, watching the inner planets spin in your mind's eye like a demonstration arranged specifically for your benefit. 4 rocky worlds, 4 different atmospheres, 4 radically different thermal outcomes, all lit by the same star. You leave the rocky inner planets behind and drift outward, past the asteroid belt with its scattered rubble of a world that never quite managed to form, and into the realm of the gas giants. Out here, the Sun is noticeably dimmer, not faint, not invisible, but diminished. A brilliant point of light rather than the overwhelming disk you know from Earth's sky. Jupiter orbits at about 778 million kilometers from the Sun, more than 5 times Earth's distance, and receives only about 1/25 of the solar energy per square meter. By the time you reach Saturn, at nearly 1.5 billion kilometers, the sunlight has thinned to roughly 1% of what Earth enjoys. You might expect these distant worlds to be nothing more than frozen spheres, passively cooling in the dark. And you would be wrong, because the gas giants have a trick that the rocky planets do not. They make their own heat. Jupiter radiates approximately 1.5 to 2 times more energy than it receives from the Sun. Let that settle in. This planet, this enormous swirling ball of hydrogen and helium wider than 11 Earths laid side by side, is generating heat internally and pumping it out into space. The source of this excess energy is gravitational contraction, this slow, ongoing compression left over from Jupiter's formation 4.5 billion years ago. When the planet coalesced from the solar nebula, gravitational energy was converted into heat, and Jupiter has been gradually releasing that primordial warmth ever since. It is cooling down, technically, but at a rate so slow that it will continue to glow with internal heat for billions of years to come. The deep interior of Jupiter is estimated to be around 20,000 degrees Celsius, hotter than the surface of the Sun, a fact that never stops being startling no matter how many times you encounter it. Saturn tells a similar story, but with an additional flourish that borders on the fantastical. Saturn also radiates more energy than it receives from the Sun, roughly 2 to 2.5 times more, and while gravitational contraction accounts for some of this, it is not enough to explain all of it. The leading theory involves helium rain. Deep inside Saturn, where pressures and temperatures are extreme, helium becomes immiscible with hydrogen, meaning the two gases refuse to mix like oil and water. Helium droplets form and fall inward through the lighter hydrogen, a literal rain of helium descending through the planet's interior. As these droplets sink, they convert gravitational potential energy into heat, warming the deeper layers and contributing to Saturn's excess luminosity. It is raining helium inside Saturn, and that rain is keeping the planet warm. And here is where the story gets even more extravagant. The conditions deep within both Jupiter and Saturn are so extreme that hydrogen itself undergoes a phase transition, changing from a molecular gas to a metallic liquid. Metallic hydrogen is a state of matter where hydrogen atoms are crushed so tightly that their electrons become delocalized and flow freely, like electrons in a metal conductor. This metallic hydrogen layer is believed to be the source of both planets' powerful magnetic fields. It is a form of matter that barely exists on Earth, having been produced in laboratories only in minuscule quantities under enormous pressures, yet it makes up a significant fraction of Jupiter's interior. You're looking at a planet whose insides contain an ocean of liquid metal that would make any science fiction writer proud. Here is the historical fact for this section. The idea that Jupiter might have an internal heat source was first seriously proposed in the 1960s, when infrared observations revealed that the planet was emitting more thermal radiation than it should if it were merely reflecting and re-radiating sunlight. This discovery came as a surprise to many astronomers who had assumed the giant planets were thermally inert, simply sitting in the cold of deep space and responding passively to whatever sunlight reached them. The Pioneer and Voyager missions in the 1970s and 1980s confirmed and refined these measurements, providing detailed thermal maps that showed Jupiter and Saturn were genuinely warm from within. Historians still argue whether the discovery of internal heat generation in the gas giants fundamentally changed our understanding of what a planet is, blurring the line between planets and failed stars, or whether it was simply an interesting addition to an already complex picture. And here is a quirky detail that deserves its own moment of wonder. There is a long-standing hypothesis, debated and refined over decades, that the extreme pressures inside gas giants might create diamonds. Carbon, present in both Jupiter and Saturn as methane and other compounds, could theoretically be crushed into diamond crystals at sufficient depth. On Saturn, some models suggest these diamonds might form high in the atmosphere as carbon soot, then fall inward, solidifying into diamond hailstones, and eventually melting into liquid diamond oceans deeper in the interior where temperatures exceed diamond's melting point. The phrase liquid diamond ocean is not poetic license. It is a genuine, if speculative, prediction from planetary science. Neptune and Uranus, the ice giants farther out, are considered even more likely candidates for diamond rain, given their higher concentrations of carbon-bearing compounds. Laboratory experiments in recent years have successfully created nanoscale diamonds under conditions simulating ice giant interiors, lending support to the idea. Somewhere out in the cold, dark, outer solar system, it might literally be raining diamonds, falling through hydrogen skies into seas of liquid gemstone. You float between these enormous worlds, the sun now just a very bright star behind you, and you realize that the story of heat in space is not simply about the sun broadcasting energy outward and everything else passively receiving it. Some worlds are furnaces in their own right, generating warmth from deep within, holding on to primordial heat, squeezing energy from gravity and chemistry and phase transitions that have no equivalent in your everyday experience. The sun is the dominant source of energy in the solar system, but it is not the only one, and the gas giants are living proof that a planet does not need to be close to a star to be warm. It just needs the right ingredients and enough mass to keep the internal fires burning. You keep drifting outward, past Saturn's rings, past the pale blue dot of Uranus tilted on its side, past Neptune with its shrieking supersonic winds, and you head into the deep. Not deep in a gravitational sense, but deep in a thermal one. You are looking for cold now, not the moderate cold of Mars or the shadowed cold of lunar craters, but the most extreme cold that nature has managed to produce anywhere in the observable universe. And you find it, surprisingly, not in some empty stretch of intergalactic void, but inside a cloud of gas 5,000 light-years from Earth, in the southern constellation Centaurus. It is called the Boomerang Nebula, and it is the coldest known natural place in the cosmos. The Boomerang Nebula is a preplanetary nebula, a shell of gas and dust being ejected by a dying star in the process of transitioning from a red giant to a white dwarf. The central star is blowing material outward at roughly 164 kilometers per second, an astonishing speed for stellar outflow, and it is this rapid expansion that creates the extreme cold. When a gas expands quickly, it cools. This is the same principle that makes the air coming out of a spray can feel cold against your skin, or that allows your refrigerator to function. It is called adiabatic cooling, and in everyday life, it produces mildly chilly breezes and frosty cans of compressed air. In the Boomerang Nebula, it produces a temperature of approximately 1 Kelvin, 1 degree above absolute zero, colder than the cosmic microwave background, that ancient 2.7 Kelvin whisper left over from the Big Bang that we explored earlier. This is worth pausing over because it is genuinely extraordinary. The cosmic microwave background bathes the entire universe in a faint warmth of 2.7 Kelvin. Everywhere you go, no matter how far from any star or galaxy, you're immersed in this radiation, and any object left alone long enough will eventually equilibrate to that temperature. The Boomerang Nebula is colder than this baseline. It has managed to undershoot the floor of the universe. The rapid expansion of gas is carrying energy away faster than the cosmic background radiation can replenish it, creating a pocket of cold that should not exist by casual intuition. It is as if you found a room in a heated building that was somehow colder than the outdoors. The mechanism is different, of course, but the surprise is the same. Nature found a way to go below what seemed like an absolute minimum, and it did so not through any exotic physics, but through the straightforward thermodynamics of expanding gas. Here is the historical fact that grounds this discovery. The Boomerang Nebula's extreme cold was first measured in 1995 by astronomers Raghavendra Sahai and Lars-Åke Nyman using the Swedish ESO submillimeter telescope in Chile. They were observing the nebula at millimeter wavelengths and noticed that it was absorbing the cosmic microwave background radiation rather than emitting against it. This absorption signature meant the gas had to be colder than the background, which was a startling finding. Subsequent observations with the Atacama Large Millimeter Array, ALMA, in 2013, refined the measurements and revealed the nebula's detailed structure, showing that the ultra-cold region was concentrated in the outer lobes of the outflow. Historians still argue whether the Boomerang Nebula represents a truly unique phenomenon, or whether similar ultra-cold outflows might be common in preplanetary nebulae, but have simply gone undetected, because the conditions are short-lived on astronomical timescales. And here is a quirky detail that gives this cold place a strange kind of personality. The Boomerang Nebula was originally named for its apparent shape in early low-resolution observations, which showed an asymmetric, curved structure resembling a boomerang. Later, higher resolution images revealed that it is actually more symmetrical than initially thought, with two lobes extending from the central star like a ghostly hourglass, or, as some astronomers have suggested, a bow tie. But the name stuck, because astronomy has a long tradition of keeping names that no longer quite fit. Pluto is still named after the god of the underworld despite being demoted from planethood. The Big Bang was originally a derisive term coined by Fred Hoyle, who did not believe in the theory, and the Boomerang Nebula remains a boomerang even though it looks nothing like one. Science is meticulous about its measurements and charmingly lazy about its labels. The existence of the Boomerang Nebula raises a fascinating conceptual point about the nature of cold in space. We have established that space itself does not really have a temperature in the everyday sense, that the 2.7 Kelvin cosmic background is the effective thermal floor, and that objects in space equilibrate to whatever balance of incoming and outgoing radiation they can achieve. But here is a natural process that creates temperatures below that floor, a reminder that thermodynamics is not a set of rigid boundaries, but a set of tendencies that can be locally overridden by the right circumstances. The universe trends toward equilibrium, but on the way there it permits pockets of extraordinary cold, just as it permits pockets of extraordinary heat inside the cores of stars. You linger near the Boomerang Nebula in your mind, picturing its ghostly lobes glowing faintly in sub-millimeter light, colder than anything else nature has produced in the observable universe. 1 Kelvin, 1 degree above the theoretical limit of all motion, all vibration, all thermal activity. The gas out here is barely moving, its molecules crawling at speeds that would make a glacier look impatient. And yet even this is not absolute zero. Even here there is still a faint tremor of kinetic energy, a last flicker of motion that quantum mechanics says can never quite be extinguished. Which as it happens is exactly where you're heading next, deeper into the cold, closer to the unreachable bottom, toward the theoretical limit that the universe seems to guard more jealously than any other. You chase the cold downward now, not through physical space but through the thermometer itself, watching the numbers shrink toward a boundary that physics has declared untouchable. Absolute zero. 0 Kelvin. Minus 273.15 degrees Celsius, the point at which, in classical thermodynamics, all molecular motion ceases entirely. No jiggling, no vibrating, no spinning, no translating through space. Perfect stillness. The ultimate cold, and you cannot reach it. Not you personally, not humanity collectively, not any civilization anywhere in the universe, no matter how advanced. This is not a technological limitation that might be overcome with better equipment. It is a fundamental law of nature, baked into the structure of the universe at its deepest level, and understanding why is one of the most elegant pieces of physics you will encounter tonight. The third law of thermodynamics, formulated in various ways by Walter Nernst, and later refined by others in the early 20th century, essentially states that as a system approaches absolute zero, the entropy of that system approaches a minimum value, and the amount of work required to extract each additional increment of heat grows without bound. In plainer language, the closer you get to absolute zero, the harder it becomes to get any closer. Each step requires more energy than the last. The final step, from some infinitesimally small temperature to exactly zero, would require an infinite amount of work. It is like trying to reach a wall by always walking exactly half the remaining distance. You get closer and closer, but you never arrive. The wall is always there, always visible, always one more halving away. But it gets even more interesting when you bring quantum mechanics into the picture. Classical thermodynamics imagined absolute zero as perfect stillness, every particle frozen in place like a cosmic game of musical chairs where the music has finally stopped. Quantum mechanics says this cannot happen. The Heisenberg uncertainty principle, that cornerstone of quantum physics that Werner Heisenberg formulated in 1927, states that you cannot simultaneously know both the exact position and the exact momentum of a particle with perfect precision. If a particle were perfectly still, you would know its momentum exactly. It would be zero, and its position would have to be completely uncertain, smeared across all of space. This is physically nonsensical, so even at absolute zero, particles retain what is called zero-point energy, a minimal, irreducible tremor of motion that can never be eliminated. The universe insists on a final whisper of activity, a faint hum that persists even at the coldest conceivable temperature. Absolute zero is not just unreachable. Even if you could reach it, it would not be the perfect silence you imagined. Here is a historical fact that makes this story richer. The race to reach temperatures near absolute zero began in earnest in the late 19th century, driven by the quest to liquefy gases. Scientists discovered that gases could be cooled by compressing them and then allowing them to expand, each cycle dropping the temperature further. Oxygen was liquefied in 1877 by Louis-Paul Cailletet and Raoul Pictet, working independently. Nitrogen followed shortly after. Hydrogen was liquefied by James Dewar in 1898. But the ultimate prize was helium, which has the lowest boiling point of any element, just 4.2 Kelvin. The Dutch physicist Heike Kamerlingh-Onnes finally achieved liquid helium in 1908 at his laboratory in Leiden, reaching temperatures below 5 Kelvin and opening the door to a new frontier of physics. 3 years later, while studying mercury cooled to liquid helium temperatures, Onnes discovered superconductivity, the complete disappearance of electrical resistance in certain materials near absolute zero. Historians still argue whether Onnes fully anticipated the significance of superconductivity when he first observed it, or whether he initially regarded it as an experimental curiosity that would have limited practical application. Either way, his laboratory in Leiden became the coldest place on Earth for a generation. And here is a quirky detail that adds a human touch to the pursuit of absolute zero. Kamerlingh-Onnes was famously meticulous and somewhat secretive about his experimental techniques. His laboratory operated with a precision that bordered on obsessive, and he was known to guard his methods jealously, sharing details only reluctantly with visiting scientists. He even developed his own system of glass-blowing expertise within the lab, training technicians to produce the custom equipment he needed rather than outsourcing to commercial manufacturers. His motto, reportedly, was, "Through measurement to knowledge," which sounds perfectly reasonable until you realise he applied it to absolutely everything, including the management of his staff. He ran his laboratory like a small, extremely cold factory, and the results speak for themselves. Nobody else liquefied helium for another 15 years. Modern laboratories have pushed far beyond Onnes' achievements, using techniques like laser cooling, where carefully tuned laser beams slow atoms to a near standstill, and evaporative cooling, where the most energetic atoms are selectively removed from a trapped gas. Physicists have reached temperatures measured in billionths of a Kelvin, nanokelvins, temperatures so close to absolute zero that the remaining thermal energy of the atoms is barely distinguishable from their zero-point energy. At these temperatures, matter behaves in ways that have no analogue in everyday experience. Bose-Einstein condensates form, collections of atoms that lose their individual identities and merge into a single quantum state, behaving as one entity rather than a collection of particles. Superfluids emerge, liquids that flow without any friction whatsoever, capable of climbing the walls of their containers and flowing through openings too small for ordinary liquids to penetrate. You sit with this for a moment, marvelling at the strangeness. The coldest temperatures ever achieved exist not in space, but in laboratories on Earth, in vacuum chambers smaller than a shoebox, where a few million atoms hover in magnetic traps at temperatures colder than anything the universe has produced naturally. Humans, in their stubborn curiosity, have created conditions colder than the Boomerang Nebula, colder than the deepest void between galaxies, colder than anywhere else in the known cosmos. And still, absolute zero remains out of reach, guarded by the laws of thermodynamics and the quantum hum that refuses to fall silent. You've been chasing cold for a while now, down through the Boomerang Nebula's 1 Kelvin, past the nanokelvins of laboratory traps, toward the unreachable zero, but now it is time to turn around and look in the other direction. Not toward the coldest, but toward the end. The final chapter of temperature in the universe. The long, slow, inevitable conclusion that thermodynamics has been quietly promising since the first particles began to move. You're going to fast forward now, far beyond the present, beyond the death of the sun, beyond the last star, beyond the last flicker of light, into a future so distant that the numbers used to describe it stop feeling like numbers and start feeling like poetry. You are heading toward the heat death of the universe. The concept rests on the second law of thermodynamics, which states that in any closed system, entropy tends to increase over time. Entropy is often described as disorder, though that is a simplification that makes physicists wince slightly. More precisely, entropy is a measure of the number of microscopic arrangements that are consistent with a system's macroscopic state. High entropy means many possible arrangements, which tends to correspond to uniformity, equilibrium, sameness. Low entropy means few possible arrangements, which tends to correspond to structure, gradients, differences. A hot cup of tea in a cold room has low entropy because the thermal energy is concentrated in one place. After the tea cools and the room warms slightly, the energy is spread evenly throughout, and entropy has increased. The system has moved from a state of difference to a state of sameness, and crucially, it will not reverse on its own. The room will never spontaneously cool down and reheat the tea. Entropy flows one way. Now apply this to the universe as a whole. Right now, the cosmos is full of gradients. Stars are hot and space is cold. Energy flows from hot regions to cold regions, and that flow powers everything interesting in the universe. Every chemical reaction, every biological process, every thought you have ever had. But the second law says these gradients are temporary. Stars will burn through their fuel, hot things will cool, cold things will warm, if only infinitesimally. Over unimaginable stretches of time, the universe will trend toward a state of perfect uniformity, where every point in space is at the same temperature, every gradient has been erased, and no energy can flow from anywhere to anywhere because there is no difference left to drive the flow. This is the heat death, not a fiery apocalypse, not a dramatic explosion, but the ultimate and final cold. A universe at equilibrium, a cosmos where nothing happens because nothing can happen. Every star has burned out, every black hole has evaporated through Hawking radiation, a process that takes incomprehensibly long timescales. Every particle has settled into its lowest energy state. The temperature everywhere is a uniform fraction of a degree above absolute zero, sustained only by the fading cosmic microwave background, which itself continues to cool as the universe expands. There is no light, no warmth, no structure. Just an infinite, dark, featureless expanse at near zero temperature stretching on forever. Here is the historical fact that gives this idea its pedigree. The concept of heat death was first articulated in the mid-19th century by Lord Kelvin, that same William Thomson who once thought the sun might be burning coal. In 1852, Kelvin published a paper noting that the second law of thermodynamics implied a universal tendency toward the dissipation of mechanical energy, and he speculated that the universe might eventually reach a state where no further work could be performed. The German physicist Hermann von Helmholtz arrived at similar conclusions independently, using the German term Wärmetod, literally heat death. The idea provoked considerable philosophical anxiety in Victorian-era science. If the universe was winding down like a clock, what wound it up in the first place? And what was the point of human endeavour if everything was destined to dissolve into tepid sameness? Historians still argue whether the heat-death concept influenced the broader cultural pessimism of the late 19th century, feeding into literary and philosophical movements that grappled with meaninglessness and entropy, or whether it remained largely a concern of physicists and thermodynamicists with little public impact at the time. And here is a quirky tidbit that lightens this existentially heavy topic. The timeline for heat death is so absurdly long that it makes the current age of the universe look like the first syllable of an infinite sentence. The last conventional stars, red dwarfs, will burn out in about 10 to the 14th years, roughly 100 trillion years from now. Black holes will take far longer to evaporate, with the largest supermassive black holes lasting perhaps 10 to the 100th years, a number so large that writing it out in full would require more zeros than there are atoms in the observable universe. After even the black holes are gone, the universe enters what some cosmologists call the dark era, an epoch of perfect darkness and near-perfect cold that stretches on without limit. If you compress the entire current age of the universe, 13.8 billion years, into a single second, the time until the last black hole evaporates would be longer than trillions upon trillions of times the current age of the universe. The numbers are not just large, they are deliberately, almost comically, beyond comprehension. Some physicists find the heat death scenario oddly comforting. Everything that has ever happened, every star, every planet, every civilization, every moment of beauty or terror or boredom occurs in this brief, wild, low-entropy flash at the beginning of the universe's history. We exist in the interesting part, the part where gradients still drive change and complexity is still possible. The heat death is not a tragedy because it is not an event. It is an asymptotic fade, a slow dimming that takes longer than any conscious being could possibly witness. And between now and then, there is an almost infinite amount of time for the universe to do interesting things. You let that thought settle as you float in the dark, looking back toward the distant sun, still blazing, still fusing, still pouring its energy into the void. It will not last forever, nothing will. But tonight it is burning and you are here to notice. You float back toward the present now, back from that incomprehensibly distant future, and you bring with you a renewed appreciation for the fact that right now, in this cosmological eye blink, things are warm and complicated and very much alive, and they are alive in space specifically, because human beings are extraordinarily stubborn about surviving in places that do not want them. The vacuum does not welcome you. The thermal extremes do not accommodate you. The radiation would happily unravel your DNA if given half a chance. And yet, for over 6 decades, humans have been building machines and suits and habitats that keep fragile biology functioning in the most hostile environment imaginable. The engineering of thermal survival in space is one of the great unsung triumphs of the 20th and 21st centuries, and it deserves a gentle, appreciative tour. Start with the simplest and most ubiquitous solution, multi-layer insulation, often abbreviated LI. You've seen it in every photograph of a spacecraft, even if you did not know what you were looking at. It is that crinkly gold or silver foil that covers satellites, space telescopes, and sections of the International Space Station, giving them the appearance of being wrapped in extremely expensive Christmas presents. Each Meli blanket consists of multiple thin layers of reflective material, typically aluminized mylar or captain, separated by thin spacer materials that minimize conduction between layers. The reflective surfaces bounce thermal radiation back and forth, dramatically slowing the rate at which heat escapes or enters. A typical MLI blanket might have 20 or 30 layers, each one adding another barrier to radiative heat transfer. The effect is cumulative and remarkably powerful. Without MLI, spacecraft electronics would freeze in shadow and fry in sunlight within minutes. With it, the thermal swings are moderated enough for sensitive instruments to function. Then there are the heaters. Not the roaring, flame-based heaters you might imagine, but small, precisely controlled electrical heating elements placed at critical points throughout a spacecraft. When a component's temperature drops too low, the heater activates, providing just enough warmth to keep it within operating range. The Mars rovers, Spirit, Opportunity, and Curiosity all relied on electrical heaters to survive the Martian nights, when temperatures at the surface plummet far below the operating limits of their electronics. Opportunity, in particular, survived on Mars for over 14 years, vastly exceeding its planned 90-day mission, partly because its heaters and thermal management systems performed far better than expected. The little rover trundled across the Martian surface through summer and winter, dust storms and clear skies, kept alive by a thermal system designed with enough margin to handle the worst Mars could throw at it. And then there is the Voyager program, which represents perhaps the most poignant example of thermal engineering in all of spaceflight. Voyager 1 and Voyager 2, launched in 1977, are now the most distant human-made objects in existence, sailing through interstellar space billions of kilometers from the Sun. At their current distances, sunlight is far too feeble to provide any meaningful warmth. Solar panels would be useless. Instead, both spacecraft are powered by radioisotope thermoelectric generators, devices that convert the heat produced by the natural decay of plutonium-238 into electricity. These generators serve a dual purpose. They provide electrical power for the spacecraft's instruments, and the waste heat they produce helps keep the spacecraft's internal temperature above the minimum required for its electronics to function. The plutonium is slowly decaying, producing less heat and less power with each passing year, and NASA engineers have been methodically shutting down instruments one by one to conserve energy. Historians still argue whether the Voyager program represents the single greatest achievement in the history of space exploration, or whether it shares that title with Apollo. But the fact that both spacecraft are still communicating with Earth nearly 5 decades after launch is a testament to engineering that borders on the miraculous. Here is a quirky detail about Voyager's thermal management that is easy to overlook but worth savouring. The spacecraft were designed with thermal louvers, mechanical devices that open and close to regulate heat loss. When the spacecraft is too warm, the louvers open, exposing radiative surfaces that dump heat into space. When it's too cold, they close, trapping heat inside. These louvers are entirely passive on some spacecraft, driven by bimetallic springs that respond to temperature changes without any electrical input. It is a beautifully simple solution, a mechanical thermostat operating in the vacuum of space, using nothing more than the differential expansion of two metals bonded together. No software, no sensors, no processors, just physics and good design, doing their job in silence for decades. Here is the historical fact that anchors this section further back in time. The very first crewed spacecraft, Vostok 1, which carried Yuri Gagarin into orbit on April 12, 1961, had a remarkably crude thermal control system by modern standards. The capsule relied primarily on its spherical shape and a heat-resistant outer coating to manage thermal loads during re-entry, and its internal temperature was regulated by a simple fan-driven air circulation system. Gagarin's flight lasted only 108 minutes, so the thermal challenges were limited. But even in that short time, the cabin temperature fluctuated noticeably. Early Soviet and American spacecraft were essentially learning by doing, discovering the thermal realities of spaceflight through direct experience rather than comprehensive modelling. Each mission taught engineers something new about how heat behaved in orbit, and each subsequent design incorporated those lessons. You think about all of this, the foil blankets and the plutonium heaters and the passive louvers and the careful, obsessive engineering that goes into keeping a handful of circuits and a few fragile humans alive in a void that offers nothing and forgives nothing. The universe does not owe you warmth. It does not owe you air or pressure or protection from radiation. Every breath an astronaut takes, every data packet Voyager transmits, every photograph a Mars rover captures is a small, defiant victory against an environment of perfect indifference. And the thermal challenge, keeping things not too hot and not too cold in a place where both extremes exist simultaneously, sits at the heart of every one of those victories. You settle into the strange comfort of knowing how much effort goes into managing heat in space, and now you allow yourself to wander toward the edges of what we know, into the territory where confident answers give way to shrugs and furrowed brows and the honest, wonderful admission that we're not entirely sure. Because for all the elegance of thermodynamics, for all the precision of our instruments, and the ingenuity of our engineering, there are thermal mysteries in the universe that remain stubbornly unsolved. Scientists are still arguing about them in journals and at conferences, and the arguments are not about minor details. They're about fundamental processes that seem to contradict the very principles we've been exploring all night. The most famous of these is the coronal heating problem, and it has been gnawing at solar physicists for over 80 years. Remember the corona, that ghostly halo of plasma you pass through on your way into the sun's core back in Section 3. You noted at the time that the corona is paradoxically hotter than the surface below it, and now it is time to confront that paradox properly. The photosphere, the sun's visible surface, sits at about 5,500 degrees Celsius. The corona, the outermost layer of the sun's atmosphere, reaches temperatures of 1 to 3 million degrees Celsius. That is not a typo. The layer further from the core, further from the nuclear furnace, further from the source of all the sun's energy, is hundreds of times hotter than the layer below it. This is like walking away from a campfire and finding that the air gets progressively hotter the further you go, eventually reaching temperatures that would vaporize steel. It makes no intuitive sense, and it has been driving scientists mildly crazy since the 1940s, when Swedish physicist Bengt Edlund and German astronomer Walter Grotrian first established that the corona's temperature was in the millions of degrees. Several theories have been proposed. One involves magnetohydrodynamic waves, specifically alpha-Venn waves, ripples in the sun's magnetic field that propagate outward and deposit their energy in the corona, heating it like a microwave heats food, from the inside out rather than the outside in. Another involves nanoflares, millions of tiny magnetic reconnection events happening constantly across the sun's surface, each one releasing a small burst of energy that collectively heats the corona to extreme temperatures. A third, more exotic proposal involves turbulence in the solar magnetic field, dissipating energy at specific altitudes. Each theory has supporting evidence, and each has gaps. Historians still argue whether the coronal heating problem has persisted so long because it is genuinely one of the hardest problems in astrophysics, or because solar physics has been historically underfunded relative to its importance, starved of the observational resources needed to settle the question. Missions like NASA's Parker Solar Probe, launched in 2018 and currently making record close approaches to the Sun, are gathering data that may finally crack the mystery. But as of now, the corona remains hotter than it has any obvious right to be. Then there is the Pioneer anomaly, a subtle thermal puzzle that haunted spacecraft engineers for decades. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, were among the first spacecraft to travel beyond the asteroid belt. As they sailed through the outer solar system and beyond, tracking stations noticed that both spacecraft were decelerating very slightly more than predicted by gravitational models. The discrepancy was tiny, about 8 times 10 to the minus 10 meters per second squared, but it was persistent and consistent across both spacecraft. For years, exotic explanations were proposed, including modifications to Newtonian gravity and new physics beyond general relativity. The mystery lingered from the 1980s through the early 2000s, spawning hundreds of papers and considerable public fascination. Eventually, a painstaking analysis published in 2012 concluded that the most likely explanation was anisotropic thermal radiation, meaning the spacecraft were radiating slightly more heat in one direction than the other, producing a tiny but measurable thrust. The electrical systems and plutonium power sources generated waste heat, and the asymmetric design of the spacecraft meant that this heat was not emitted equally in all directions. The resulting thermal recoil was enough to account for the anomalous deceleration. A mystery that had tantalized physicists for 30 years turned out to be, at its heart, a problem about heat not being evenly distributed on a spacecraft. The universe's sense of humour is subtle but persistent, and here is a quirky detail from the frontier of planetary science that does not yet have a clean explanation. Several moons in the outer solar system are warmer than they should be, based on their distance from the Sun and their known energy budgets. Enceladus, a small moon of Saturn barely 500 kilometers across, has geysers of water ice erupting from fractures near its south pole, powered by an internal ocean of liquid water kept warm by tidal heating. But some calculations suggest that the observed heat output is greater than what standard tidal heating models predict. Something is keeping Enceladus warmer than the math says it should be, and nobody's entirely sure what. Jupiter's moon Europa presents a similar puzzle, with a subsurface ocean maintained by tidal forces, but with thermal details that do not perfectly align with models. These warm little worlds orbiting in the frozen outer reaches of the solar system are reminders that the thermal story of space is not finished being written. You sit with these mysteries the way you might sit with a good riddle, not frustrated by the lack of an answer, but quietly delighted that the questions exist at all. The coronal heating problem tells you that even the most familiar object in the sky, the Sun, harbours secrets we have not cracked. The Pioneer anomaly tells you that something as mundane as waste heat can masquerade as new physics for 3 decades. And the warm moons of the outer solar system tell you that the universe is more thermally creative than any simple model can capture. This is the beautiful honesty of science. It does not pretend to have all the answers. It maps the boundaries of what it knows, labels the unknowns clearly, and keeps looking. And in the spaces between certainty and mystery, there is room for wonder, which is really just another form of warmth. You begin the long, gentle glide back now, back from the unsolved mysteries, back from the frozen nebulae and the raining diamonds, back from the thermosphere's paradox and the sun's impossible corona. You're retracing your steps, and as you do, the pieces of tonight's journey settle into place, like stones in a mosaic, each one finding its spot, each one necessary. The question was simple: why is space so cold when the sun is so hot? And the answer, as it turns out, was never really about cold at all. It was about emptiness. The sun is a thermonuclear furnace converting 4 million tons of matter into energy every second, and it has been doing so for 4.5 billion years with the patience of something that has no concept of patience. It sends that energy outward in every direction as electromagnetic radiation, photons streaming across the vacuum at the speed of light, carrying warmth that will not become warmth until it lands on something. And that is the heart of the matter. Space is not cold the way a freezer is cold, filled with frigid molecules actively pulling heat from your skin. Space is empty. It has almost nothing in it. And temperature, as you discovered when you shrank down to the molecular level all those sections ago, is the average kinetic energy of particles. Where there are no particles, or almost none, the concept of temperature becomes thin and ghostly, a measurement with nothing to measure. You remember the campfire where you learned that conduction needs contact, convection needs fluid, and only radiation survives the void. You remember Mercury's 600-degree thermal swing, the moon's razor-sharp shadow boundaries, the astronauts who overheat before they freeze. You remember the greenhouse effect, hero turned villain, the thin atmospheric blanket that separates a living world from a frozen or scorched one. You remember the cosmic microwave background, that 2.7 Kelvin whisper left over from the Big Bang, the faint hum that fills every cubic centimetre of the observable universe and sets the temperature floor of the cosmos. You remember the Boomerang Nebula, 1 degree above absolute zero, colder than the background itself. A pocket of extreme cold created by nothing more exotic than rapidly expanding gas. You remember the gas giants with their internal furnaces, Jupiter radiating more heat than it receives, Saturn raining helium through its metallic hydrogen depths. You remember absolute zero, the unreachable limit guarded by thermodynamics and quantum mechanics, and the laboratories on Earth that have crept closer to it than anything in nature. You remember the heat death, that unimaginably distant future when every gradient has been erased and the universe settles into cold, silent equilibrium. And you remember the engineering, the foil blankets and plutonium heaters and ammonia cooling loops that keep human beings alive in an environment that does not care whether they live or die. The sun is hot, space is empty, and the emptiness cannot be warmed because there is nothing there to warm. That is the answer. It fits in a single sentence. But understanding it, really understanding it, required this entire journey through stars and atoms and centuries of human curiosity. It required Joseph Fourier wondering why the Earth was warmer than it should be, and Fraunhofer discovering dark lines in the solar spectrum, and Penzias and Wilson cleaning pigeon droppings out of an antenna. It required Lord Kelvin being magnificently wrong about the sun burning coal, and Arrhenius being cheerfully wrong about warming being a good thing. It required every scientist who ever pointed an instrument at the sky and asked a question they did not yet have the tools to answer. Here is one last historical thought to carry with you. The ancient Greek philosopher Empedocles, around 450 BCE, proposed that the universe was governed by two forces, love and strife. Love drew things together. Strife drove them apart. He was talking about something mythological, but if you squint, he was also talking about thermodynamics. Energy flows from hot to cold, from concentrated to dispersed, from structure to uniformity. The sun pours its energy into the void, and the void dilutes it across an ever-expanding cosmos. Love creates the gradients. Strife erases them. Historians still argue whether Empedocles should be considered a proto-scientist or a poet with philosophical ambitions, but his intuition about opposing forces governing the flow of nature has aged remarkably well. And the quirky final tidbit: when you look up at the night sky and see stars, you are seeing the universe in its low-entropy youth, still burning, still structured, still interesting. Every point of light is a pocket of concentrated energy surrounded by cold emptiness, and the contrast between the two is what makes everything possible. Without hot stars and cold space, there would be no gradients, no energy flow, no chemistry, no biology, no you lying in bed listening to a story about why space is cold. The answer to tonight's question is also, in a roundabout way, the answer to why you exist. You are a product of the temperature difference between a star and the void, a brief and beautiful consequence of the universe not yet being finished cooling down. You float gently now, descending back toward Earth, back toward the blue marble wrapped in its thin, precious atmosphere. The sun is setting on whatever hemisphere you're imagining, painting the sky in oranges and pinks, scattering photons through the gas molecules that keep you warm and breathing and alive. And now the journey softens, the pace slows. The words grow longer and quieter, like footsteps on a carpet of deep snow. You have travelled from the surface of the sun to the emptiest reaches of the cosmos, from the birth of the universe to its eventual silent end, and now it is time to rest. The questions have been answered, or at least explored with honest curiosity, and the mysteries that remain are not urgent. They will wait. They have been waiting for billions of years already, and they are in no hurry. You can feel the pillow beneath your head, the gentle weight of the blanket across your chest. The room is dim, the air is still. Somewhere, the faint hum of a fan or the distant murmur of a city reminds you that you're here, on this warm little world, protected by a thin shell of gas from the enormous, empty, silent cold that stretches in every direction beyond the sky. The sun will rise again in a few hours, sending its ancient light across the void to find you, and you will feel its warmth on your face without thinking about the journey those photons took to reach you. But tonight, you know. You know why space is cold. You know why you are warm, and that is enough. Let your eyes close. Let the last image be the soft glow of starlight on the edge of the atmosphere, a thin, bright line between everything and nothing, holding the cold at bay while you sleep. Good night. Sweet dreams. The universe will still be here in the morning, still burning, still cooling, still magnificent,